Hello, in this breakout session, which is part of work package 15 of promotion, I will be talking about testing of 320 kV HVDC GIS prototype installation, which we have carried out in KEMA Labs as part of promotion project. First, I would like to introduce myself. My name is Nadew Belda. I'm Innovation Engineer at KEMA Labs. I've joined KEMA Labs in 2015. I'm responsible for development of test methods, design and implementation of test circuits for HVDC switchgear. I've been active in promotion projects, not only in work package 15, also in other work packages, work package 5 and 10. Where I was responsible for testing of HVDC circuit breaker. I was also task leader for several deliverables of work package 5 and 10. Well, the content of my presentation includes the following points. First, I would like to give a brief introduction of a prototype installation testing. Basically, this is discussed in detail with another presentation. And then try to describe a test object, which is a 320 kV HVDC GIS as it is installed in our laboratory, and then present about test program that we have followed, and finally the test results. Coming to introduction of a prototype installation test. Before that, I would like to mention a few words about other kinds of tests. Of course, I think this will be presented in detail in another presentation. There is a development test, which is focusing on a proof of concept or finding out if a specific development or a product is suitable for some applications. There is type test, which is focusing on rated performance demonstrations, so verifying under rated current and rated voltage if part of GIS or GIS assembly can fulfill those rated performance requirements. And there is a routine test, which makes sure that a given manufactured product doesn't have any kind of anomaly during manufacturing process. So this should be this is a checking process. And on-site test is, which is a commissioning test of an installation or a setup before it is put into service. But a prototype installation test is different in a way. It's broader, it's more testing under a real application condition. Actually, it's like in service operation. So it's a full-scale GIS including many different components, measurements, sensors, and other components like earthing switch and disconnectors are included. And the test itself is a long-term test. This lasted for more than a year. And during this time, all the stresses are represented, including electrical, thermal, and mechanical stresses. There are other also optional tests like partial discharge monitoring and diagnostics and checking, of course, and applying impulses and superimposed impulses as well. Well, at the end of prototype installation test, it's expected that the confidence of the user will boost significantly because it's under real operation condition, as I mentioned. And as a result of this, for example, for HVDC GIS, the technology readiness level of this product has been increased from 6 to 8 as a result of the test. And the test itself is not only an equipment, it is also a test of production, installation, and commissioning itself, because it involves all these activities, and trying to also mimic a long-term operation condition, because HVDC GIS will be operating for a number of decades in application. Here you see an impression of a test object, an HVDC GIS, consisting of several parts. For here you see the high voltage connection point, the DC bushing through which an HVDC source is connected to the bus duct. And then there is another bushing which is kept as an option for extension purpose, of course. And then the GIS is put under real surface condition, as I mentioned. That means there is current running in the conductor, in the bus duct, of course. This current has been supplied through conventional current transformers. 3 current transformers are indicated here, which are used to induce current of about 4,000 amps to heat up the bus duct, which, as a result of which, you will also measure some temperature elevation on the enclosure. And then the rating specification has been mentioned as shown here. Of course, the GIS is rated for 320 kV nominal voltage, and this corresponds to rated continuous voltage of 350 kV. Impulse voltage of 1050 kV is specified. This impulse voltage has been applied on top of DC 350 kV in both polarities. A switching impulse of 950 kV is also specified for this, and this has been applied as well at different stage of testing. And rated DC withstand voltage for example, in this case 610 kV for short duration. And then the system is rated for 4000 amps load current. It can also withstand rated peak withstand current of up to 160 kA for short duration. For example, rated short time withstand current of 64 kA for 1 second, for example, in this case is specified. And the device can operate in ambient temperature in the range between -30 to +40 degrees Celsius. In this slide, I would like to present a test program that we have followed during this long-term test of HVDC GIS. Of course, the test program has been developed based on recommendations from SIGRE and also some wishes of end users. Before putting the HVDC GIS under long-term test, there are some steps that must be followed. In this case, it's a pre-test. In the pre-test, current is run through the bus duct to see, for example, the thermal cycle. How does the temperature of the enclosure varies depending on the current? And then there is lightning and switching impulse applications, plus also partial discharge measurements under DC as well as under AC voltage. Also, lightning and switching impulse have been superimposed onto the DC voltage. That is what we call superimposed impulses. And also for a few hours of DC voltage application of both polarities, for example 120 minutes positive polarity, another 120 minutes negative polarity, and so forth. After the pretest, which is basically a check procedure that HVDC GIS is ready for long-term test, then it is put under of course the actual test, and the actual test has 6 blocks, each block lasting for 60 days. And there are different load conditions. There is a zero load and a high load. And zero load means the DC GIS is put under a DC voltage, but there is no current running in the bus duct. The high load means the DC GIS is subjected to the DC voltage plus a current of 4000 amps running through the bus duct. So here you see zero load has had 2 blocks basically. Corresponding to positive and negative DC voltage. High load has been performed 4 times, twice for each polarity. And in between each block, at the end of one block, there are also other tests. For example, lightning impulse superimposed onto the DC, and close and open operations of switch disconnectors and everything switch in that case, and also partial discharge measurements have been involved. And then of course the whole cycle has been successfully completed because at the moment of speaking this test has been finished, and the main test blocks are followed by a load cycle. In the load cycle the current is varied between zero load to high load, and this has been performed in two blocks, each block lasting for 15 days, which corresponds to each polarity. So 15 days positive polarity, 15 days negative polarity, while the load current is varying between 0 and 4000 amps. After the load cycle, there is subsequent test. Subsequent test is just to check the condition of the HVDC GIS after the test has been finalized. In this case, there are measurements of partial discharges under AC and DC conditions. There are also impulse applications, lightning and switching impulses, of course, also superimposed. Before I go into the test results, I would like to show you here the monitoring system that have been used. Of course, many monitoring system has been on board this HVDC GIS. For example, gas pressure check, partial discharge sensors have been put onto the device, arc detections in case if there is some flashover inside of the GIS tank. And also temperature, enclosure temperature has been measured at different locations. Here you see the thermocouples where they are placed, also trying to find out in comparison to the ambient. So there are thermocouples just placed in the ambient, in the neighborhood of the GIS to see the differences between the enclosure temperature and the ambient. There are disconnector and switch or earthing switch panels to show, of course, if they are in a closed and open position. Of course, the measurements of voltage and current temperature have been recorded, and this is available, and you will see that in the test results later. So a bit more about the three load cycles now with measurement results. This is taken randomly of, for example, measurements for 6 hours of temperature and current, for example, at high load, which is what you see on the left side, bottom graph. 4000 amps of current under 420 kV DC voltage. One thing I did not mention is long-term DC voltage was chosen to be 420 kV. This is to compensate for the long-term long-term aging effect of HVDC GIS under real application, because this test lasts for 1 year, but to compensate for long-term, the voltage has been increased by 20% more than the rated continuous voltage mentioned at the beginning. So here you see enclosure temperature being higher than the ambient temperature by a little bit more than 20 degrees Celsius. And on the right top you see zero load testing block just for certain hours. Of course, the temperature is ambient as you see it here, and there is no current, only the voltage has been applied, a voltage of 420 kV, in this case negative polarity. The third, which was in 15 days blocks, of course, the third test is a load cycle where current has been varied between zero load to high load as you see it. So a specific load profile for 24 hours has been specified, and that is followed to see the temperature of the enclosure, which you see it varying according to the current in this case. Yeah, some test results. Before the test results, you see the photo of the HVDC GIS under test. Well, on the right side of this photo, you see a DC source connected to the bushing of GIS. So 420 kV is supplied from there, and there is an impulse generator on the right side which can generate lightning as well as switching impulse. This has been superimposed through a spark gap. There are different methods. We use the spark gap method. For example, a capacitor coupling method could be used. And on the left you see test results, of course, lightning superimposed onto the DC voltage and switching superimposed onto the DC voltage of both polarities. That's what you see on these graphs. And of course the test circuit is shown on the top right. Well, on many occasions, of course, people are invited to see the test when the test object is live or under stress. Of course, it was one of the purpose of promotion to demonstrate, to show to the different stakeholders what's going on. And this photo was taken when a lot of people were invited to take part in demonstration of HVDC GIS. Well, a bit about test results. Of course, all the different stages of testing, the pre-test, of course, the load or the blocks of load tests, and subsequent tests have been successfully completed. At the pre-test, as I mentioned, there are different measurements: partial discharge measurement, also application of lightning and switching impulses. During the long-term load cycle tests, twice zero load and 4 times high load has been performed, and also twice load cycle has been performed, which were successfully completed. And of course, subsequent tests to check the condition of the test object has been performed, which was also included AC, DC, partial discharge measurement, lightning impulse of different polarities. And then of course visual inspection during disassembly, which showed no trace of any kind of damage, and this shows a complete successful demonstration of HVDC prototype, GIS prototype installation. Thank you for your attention, and of course I can be reached with this with the email you see on the screen in case of any question. Thank you.